Okay. So can you see the screen? Let me see, put it in slideshow. Okay, can somebody tell me whether you can see this?
We can see the screen.
Thank you. Sorry, I was muted. I'm sorry, Alex. I wanted to turn off my video. Okay. So can you hear me? Can you see the screen? Somebody?
Yes.
Thank you. Sorry for this. Okay, so as I was saying, this tutorial is going to be in two parts, mainly because it is a very wide topic. It's a very well researched topic. It's kind of a mature area, these probabilistic graphical models, which is part of statistical machine learning. And the next tutorial is actually assuming that you have heard the material here. In this material, we're going to describe what we call probabilistic graphical models. We'll see some examples, and in the next tutorial, we'll see when we have a model, how we can train and perform inference with that model. Okay. So for this tutorial, I'll give us a brief motivation of why we need probabilistic graphical models and how why they have been so successful, several applications of probabilistic graphical models, and then we go on to the core of the presentation, which is different graphical models, their representation, as well as some their properties. So motivation for graphical modeling. I'll start with something that probably everybody knows. When we try to solve a real world problem using mathematics, we usually define a mathematical model of the world. For example, in my first formula, I have a linear formula that says the x variables or values that are defined with the x vector have a linear relationship with the y variables on the right. Okay. Now, often in the real world, when we are trying to model something, it usually has a lot of uncertainty. For example, say that we are trying to predict house prices and we use different environmental factors for that, whether the price of the house will go up or down if a new subway station opens, will have a big, some certain uncertainty. We're not sure, we hope, because people will start walking around the area more, but this is not this area will become more popular, but it's definitely not certain or something. So to deal with that uncertainty, we usually model the world in the form of a probability distribution. Probability distribution, as we know it from the statistics. So the previous relationship, we will write it that there is a probability distribution that that models the variables x and y's. In that case, because we're talking about probability distributions, x and y's are not just values; they're what we call random variables, what they call in statistics random variables. Okay. Now, so what is the challenges when we say probabilistic modeling? Basically, we mean that I'm trying to model the real world using a probability distribution. And in machine learning, the definition is very similar. Okay. Now, what's the challenges with this? I'll start with a simple example. Say that I have want to predict whether a particular text, say in email, is spam or regular spam, regular email. I'm sorry. And I'll use for that the content of the email. That means the words of the emails. So in order to do that, I'm going to create a probabilistic model that connects the input, which is the word occurrences in the email, with a label that says whether this email is spam or non-spam. Okay. In this case, how I'll do that is that I'll define a probability distribution with one variable will be the label of spam or spam, and the rest of the variables, they're going to be all representations of the words in the text. And why I say representations is because a mathematical model does not understand text. So what we need to do is that we need to take a word and represent it with a form, numbers, vectors, matrices, that a mathematical model can understand. In this case, what we're going to, so in our case, where axis is the representations of the word occurrences, each x represents English word, and we represent it with a binary variable that says whether this word is present in the email. Okay, and the binary, we also have the variable y, the label that we said, which says whether the email is spam or not. And this is a binary variable 0, 1, 0, spam, 1, non-spam. So in order to classify the new email, so we'll define our model, this P of theta, where P is a probability distributions. We'll train this model. This probability distribution is usually having some parameters that we have to learn. Once we learn it, and then a new mail comes, and we want to say whether it is spam or not, we look at the probability of P y equals 1. Well, in this case, 1 for me is the spam, given all the instances of the other variables. So what kinds of words exist are present in the email. Yes, in the last email. Now, one thing one can easily see from here is that the domain that's where the all the y variables take their values from is quite large. It's going to be 2 to the n plus 1, where n is the size of the English variable. The plus 1 is because we also have the y, which is 2 more variables. Okay, so in order to be able to define this probability distribution, say that we need to find all the probabilities for all these combinations, that's a very hard problem in practice, because as we said, all these combinations is the sum of these combinations is large. It's going to be 2 to the n, where n is the size of the English vocabulary. That's n is to the thousands. I don't know exactly how many English words exist and how many we're going to use, but definitely it's going to be in the thousands. Now, on the other hand, independence among variables can significantly decrease this domain. For example, we know that we don't need to define dependencies between, for example, say cleaning and I don't know, sheep, because they're probably independent. On the other hand, there are some other variables that are dependent and in which we need to define their dependence. And when we say the dependencies here, we mean that we need to define a probability distribution that contains both of them. Okay. So, and this is basically a simple statistic. So if all of them are what is called independent, then we can define the probability distribution P theta as the multiplication of all the independent combinations, and then the domain becomes much smaller because the smaller multiplants will have a smaller number of variables, in which case the domains will be smaller because the global domain is going to be the sum of all these domains. Okay. So, and that's where probably graphical models come in place, is that it is a computer science construct that makes this, enables expressing these independencies in a very structured way. And more important, once the modeler can define these independencies, then automatically there exist inference and training algorithms that take into consideration these independencies and become more efficient. Okay, so in the case of what I was discussing here, if we know something, for example, that the probability of the label of the label being spam or spam. No, the probability of its input is independent given the label, and I'll explain what it is. Then the probability that I wrote before, it can be defined as the multiplication of all the probabilities of all each independent variable. Now, so what this would mean, which is an assumption that probably cannot make here, it's oversimplified, but there is a classifier that's actually making this assumption, is that if I know the label, then what is called the probability of the word that produced this label is independent of the probabilities of all the remaining words. For example, this would be true if, for example, I have some word there, like read a flag, somebody puts a flag in the email that says, if you see this flag, say, hooray, this email is always spam. Okay, so that would be one case that this would mean that. Or, for example, there are specific words that don't really exist, and if you see them in the email, then you can classify the email as spam or non-spam without being completely independent of whatever the other words are. Okay, any questions here? And one thing I want to say also is that these independencies, we represent them with the form of the graph, and the graph is not only a notational structure that we just represent the independencies, but also once we have this graph of independencies, as I said, there are computer science machine learning algorithms that take into consideration this graph, which defines the independencies and can perform more efficient inference and training. Okay. So, having said that, the probabilistic graphical models, one example we saw is in the previous slide, is a powerful framework for representing or modeling complex real-world domains using probability distributions. They bring together graph theory and probability theory. Graph theory is because we represent some of the dependencies between or independencies between random variables using a graph. Probability theory, because this graph, along with formulas, because the graph is not enough to represent the whole probability distribution, is represent, so the graph along with some formulas represent probability distribution. So probability distributions come from probability theory. So they bring together graph theory and probability theory. It is a flexible framework for modeling large collections of random variables with complex interactions. The flexible here means that this graph, certain graphs, or anyways, the graphs that we are going to see can describe a lot of different dependencies, dependency relationships or independency relationships. They explicitly represent these independencies between variables. And I want to say here is that we say dependency, but from the graph, what we really can deduce is independence between variables, and we'll see that. They leverage graph representations to discover efficient inference and learning algorithms. I told you that once you have defined the graph, computer science or machine learning algorithms exist that take into consideration that graph. And one thing that we are not going to see here is that some of these graphs, in particular, one example that we saw where it has directions in the edges, forms the basis of one branch of causality theory. Okay, so this is very important because causality theory is an important topic and it's one of a very hard topic to tackle. Okay. Now, applications, so there are a lot and different. The reason for this is that before deep learning, it was probably the only way to represent large amounts of data, variables, not data variables. So in different domains they've been used, for example, in image processing, where each pixel could be represented with one random variable. In audio, information theory, in computer science, the example that I show you, actually the one that we said, we made this unrealistic assumption that a word, an occurrence of a word is independent of an occurrence of another given the label, is used in one of the very first classification models, the naive based, and Bayesian models, which is one form of this graph neural networks, probabilistic graphical models, and which we are going to see, have been used in Gmail spam filtering algorithm. And some variations of this are still used in computer networks, mainly to do time scheduling. In science, anywhere that there is a structured information, structured representations of different values of variables, for example, in computational biology or genetics. In healthcare and medicine, notably in disease diagnosis, where also causality is important if possible and can be established, and in transportation for traffic analysis, where different variables define different actors, cars, buses, pedestrians, traffic lights, and the graph defines the dependencies between them. Okay. Now, here I'll stop because this was the large introduction, and then I will go into the actual model representation. We see some examples, and I will ask if you have any questions on so far.
Yes, one question, Foula.
Yes.
Are log linear models considered one case of probabilistic graphical models?
That's actually a very good question. So the log linear model basically says what is the form of the probability distribution. Okay, so if how to say, a graph can describe let me see, I would say all the log linear models, but it's kind of, how to say, they're kind of orthogonal, because the graph, probabilistic graphical models define the graph and the functions, and the log linear models, they are just the functions, the probability distributions. The log linear says that the log of your variables is linear. Okay. And we're actually going to see an example, but log linear have been extensively used for probabilistic graphical models because they enable efficient training and inference, basically inference.
Yeah, that's clear. Thanks.
Okay. Okay. So going on for graphical model representation. So in probabilistic graphical models, the relationships between random variables are described by graphs, whose properties, the connectivity, the tree width reveal probabilistic and algorithmic features of the models. For example, independence and learning complexity. Basically, these are the two things that they reveal. Variable independence, and give an idea of how hard is to learn the model, to train the model, and also to perform inference, because in this model, train and inference, the algorithms are kind of they're not independent. They're we'll see it in the next tutorial. So the two main categories of this is what is called directed graphical models, where they employ directed graphs, excuse me, and directed graphs describe causality relationship between random variables. So that means that if I have an edge, which is a direct edge, the one node, for example, the source, is, the target depends on the source with a causal relationship. That means that the source is causing something related to the target variable. The other one big category is undirected graphical models, which, as their name implies, they employ undirected graphs. Examples of them are moralized graphs. We'll see what it is. They're undirected versions of direct graphical models. Conditional random fields, we'll see it's a discriminative incarnation of undirected graphical models. And what is discriminative here? so the ones that we'll see in the beginning, all the variables, what we will be, representing is the, how do we call it? Joint probability distribution, while for the conditional random fields, we'll be defining probability distributions given some variables. That's the conditional probability distributions. Then factor graphs, which are, there's not a new, there is not new type of and the graphical models, but it is a different representation which makes inference almost practical, like going from very hard to practical. So they're very important in the representations of these models, and you can represent both direct graphical models and undirected. We'll see examples. Latent variable models, which are either directed or indirect graphical models, where some variables are never observed. And then we'll finish with examples of models with continuous variables. So while I start, until I go to the last slide, we'll make the assumption that all the variables that we have is they are discrete variables, either binary or with a finite number of values. Okay. So the direct graphical models, they're also called Bayesian networks. So if you see direct graphical model of Bayesian network is exactly the same model. It is a directed graph. Sorry, I don't think, okay. A direct graph where it has nodes and edges, and the edges are directed. Each node represents a random variable. And there is also, in addition to the graph that we'll see, we can describe as a graph structure, we'll see, it also has a conditional a set of conditional probability distributions, where for every node, we define the probability distribution of this node using given its parents, you will see, and then the joint probability distribution is going to be the multiplication of all these conditional probability distributions. Okay, so basically what it says here is that we'll define a graph, that the graph describes a set of independent variables among themselves. We'll define the probability distribution for these independent sets of variables, and then in that case the probability distribution, the joint probability distribution, is going to be the multiplication of that. And just for nomenclature, we say that a probability factorizes over a DAG, a G. The DAG here is a direct graphical, a direct acyclic graph. A direct graphical model is a direct a cyclic graph, if it can be decomposed into a product of factors as specified by G. That means that if it can be decomposed, so that the dependencies that we see from this decomposition are represented in G, are similar, not similar, we can see them in the graph structure. Okay. That's a lot of words, and we will see a simple example. So for this one, I used a very simple example where we have 4 different variables. One is for a person, we define here whether a person is smoking, whether a person has cancer, whether a person has bronchitis, and whether when the person goes and does X-rays and has abnormal X-rays, they're not a healthy person. So here I make an assumption that if person is smoking, then with a high probability, it's going to develop lung cancer. It has a high probability comparing to a person who is not smoking, or it can also develop bronchitis. Okay, and also when a person has lung cancer is it may cause his or her X-rays to look abnormal. Okay, So in this case, because I defined a set of causal relationships that smoking causes cancer or bronchitis, and lung cancer and bronchitis, and lung cancer causes abnormal X-rays, I've already defined a graphical model where the nodes is all these conditions: smoking, lung cancer, bronchitis, and abnormal X-rays. Excuse me. And the edges is the relationships between its variables, as I defined, that smoking causes lung cancer. So there is an edge between smoking and lung cancer. And also each edge has a direction showing where what causes what. So in this case, I said the source causes the target. The smoking can cause lung cancer. Is clear the graph structure, how it was created? Okay, yes. Now, so we define the graph, which defines this causality relationship. So this is our Bayesian network. But also we need to define, as we said, the sets of probability distributions that describe this each of the variables here. So, and because here we're talking about discrete probability distributions, the parameters that we are going to use for these discrete probability distributions is basically the probabilities themselves that we'll have to find. So for smoking, smoking does not depend on any of the other function of the other variables. So I define a probability distribution just for this variable. So I need to have this variable has two values. So I need to have basically two variables, which is the probability of whether a person is smoking and the probability of whether the person is not smoking. And also because this is probabilities, we know that their sum is equal to 1, in which case if I know the one, then I can deduce the other. So in this case, I say that the probability of a person smoking is 0.2. So the probability of a person not smoking is 0.8. Which is actually a little bit high, but let's assume that we are in a world with heavy smokers. So then I'm going to define the probability distributions of has lung cancer. This, as we said, the has lung cancer, this variable depends on whether the person is smoking. So we need to define two different, two conditional, well, a conditional probability distribution, which is the person has lung cancer given that the person is smoking. Okay, so then we have to define basically four probabilities, which is the person has lung cancer whether given that the person is smoking, the person does not have lung cancer given that he's smoking, and the person has less cancer given that the person is not smoking, and the person has does not have lung cancer given that the person is not smoking. Actually, there is a typo here. The last one is F. So with these four probabilities, we defined the probability distribution of the person, what is called the person having cancer. And because also this is probability distributions, all the conditional distributions, we know that their sum is equal to 1. So if we know the one condition, the one value for the conditional distribution, we can deduce the other. And that way we can also create the probability distributions of all the rest of the variables, has bronchitis and has abnormal rays. Now, once we define all these conditional probability distributions, the joint probability distribution of the graph of this Bayesian model is going to be the probability distribution with smoking, has lung cancer, has bronchitis, has abnormal and rays, and it's going to be, as we said, the multiplication of all these conditional probability distributions that we just defined. And that, having defined that, we have defined the what is called the Bayesian network model or the direct graphical model. Now, in practice, we probably do not know these probabilities, so we're going to deduce it from their data. Like, we don't know what's the probability of having lung cancer given that the person is smoking. And that's why I said the parameters of this probability distribution, they're actually the probabilities. So in practice, we'll have some data, like a group of people, some of them having lung cancer, have some of them healthy, some of them having bronchitis, and we will perform inference in order to identify the values of these probabilities. Okay. Now, as we said, yes, I just said it, that having defined all these conditional probability distributions and the graph, we know that the joint probability distribution of all these variables. And when we say that, why is this joint probability distribution? Because when we define the joint probability distribution of all the variables, then we basically have all the information that to represent this group of variables. That's why it's so important, the joint probability, again, from statistics. So in this case, it's going to be the probability of smoking multiplied by the probability of lung cancer given that is smoking. Well, I didn't say, given the variable is smoking, multiplied by the bronchitis given conditional on the smoking random variable, and multiplied by the has abnormal X-rays conditional on the has lung cancer. Okay. Now, here's an example. So if we having this probability distribution, it can be represented with just 7 parameters. And the reason it is 7 is because it is the number of parameters that we need, the sum of the parameters that we need to define its multiplant. So, for example, the probability of smoking. In addition, with the constraints that because these are probabilities, the sum of them is 1. So if we know some of them, we can deduce some of the others. So while if we were trying to deduce the probability distribution of the joint probability distribution in a straightforward way, it's going to be 2 to the 4 minus 1, again minus 1, because the joint probability distribution is a probability. So the sum of all of them is going to be 1. So we need 1 less to define, which is going to be 15 parameters. So even in a very small example, as I saw here, with just 2 or 3 conditions, and all of them being binary, the number of parameters that need to be described to describe this probability distribution becomes smaller. And this effect is multiplied with a larger number of variables, which is usually the case for direct graphical models, and with larger domains. Okay. I'm sorry. Here. Now, before finishing with directly graphical models, I want to describe the types of dependencies, independencies. I keep saying dependence, but what really the graph describes is independencies. So what are the types of dependencies that the directed graphical model can describe? There are basically 3. The one which is called cascade, it's an example A and B. So in this case, we see that there is a line of variables, each one, or a sequence of variables, each one dependent of the previous one. So in this case, so let's get the X is causing the Z, and Z is causing Y, or Y is dependent on Z, and Z is dependent on Y. In this case, what we know is that X and Y are independent given Z. The other one is common parent, like our very first example that we saw with spam, where this is an example showing in C here, where 2 variables have a common parent. In this case, given the value of the parent, X and Y are independent. And what is called the V structure, which is very common that we see, is X and Y have a common child. In this case, it's a different thing, is that the X and Y are independent if z is unobserved. If we have observed the z, then these variables become dependent. And then these rules are applied recursively, and by applying these just three rules recursively on larger graphs, we can identify all the independencies that are described by the direct graphical model. Okay. Before continuing on the indirect graphical models, any questions on the Bayesian networks? Okay, so indirect graphical models, the other name of them is Markov random fields, or MRFs. It is well, I'm not going to say graph, it's a probability distribution over different variables, which can be represented by an undirected graph, in which every node, as in the case of direct graphical models, represents a variable. The joint probability distribution of all the variables in that node, in that graph, has the form that is shown here, which is a multiplication of functions along with z, when z is a normalization function. So before going to z, let's see what is the multiplant functions. So the such function is defined over a click in the graph, and a click in the graph is a subgraph of the original graph, where it's a fully connected, basically, subgraph of the original graph. And so we have to identify all the clicks and define a function for all the variables in that click. And usually these functions, they are called non-potential functions, and they are non-negative. The reason we want them non-negative is so that we can define a probability distribution. Probability distribution is a function which is non-negative, and the sum of the domains, or the integral, sums up to 1. And then we also have a partition function. It's called partition, but it's basically a normalization constant, so that we ensure that this distribution sums up to 1, because we want to define a probability distribution. And what is important here is that these potential functions define related variables that and somehow quantify the strength of their interactions. So you see here, there is no, they're related variables, but we don't know how they're related. They don't need to be dependent of each other. So these potential functions basically give you quantify how strong these relationships, that they're very related or less related. Okay.
But Foula, one question. So what is C? Why are we talking about clicks? Why is this important?
Oh, because the independence relationships are defined because over the clicks in that graph. So basically, all the variables within that click are independent of the rest of the variables. Okay. So that's basically how you define that. It makes more sense when we see simple graphs like trees or sequences. Okay, it becomes more complicated when. That's basically I haven't described how we define that, but that's basically the definition of an indirect graphical model. Okay.
So Foula, if possible, in the same direction with the question of Themis, if we multiply the function phi of nodes that aren't in a click, not connected to nodes or variables.
Yeah, we don't need to multiply exactly because they are independent. So so that is the multiplication that we create, the independence. That's how we use the independence assumption in order to partition the probability distribution into different variables, into different functions.
Okay.
Is that the question?
Yeah, thank you.
But then, as you'll see, because of the normalization constant, these variables, they're not, these functions, they're not independent of each other, the domain of these functions. because the partition function is defined over all the variables.
Okay.
So that's where the complication comes. Okay. Now, before going to these complicated things, let's see an example of, hopefully, it is a simple example that can make sense of these indirect graphical models. Now, one thing here is that with this tutorial, we're trying to squeeze what's called a course of a quarter or a semester. So it has to be a little bit compact. So I can only give you how to say high level details, not details, information, but I'll try for you to understand how these things are used. So a simple example here is that I have 3 friends, Alice, Bob, David, and Charlie, and I want to, excuse me, actually they're not 4 friends, but they're not all friends with themselves. Like Alice is friends with Bob and David, and Charlie is friends with Bob and David as well. So, but he's not friends with Alice. They don't know each other. It's not like they hate each other. So, and we have these 4 people, and we want to model what's their probability of what they're going to vote. Okay, say that as we say, we have an MRF to model voting preferences of 4 people, Alice, Bob, Charlie, and David. And we assume that the election is against 2 candidates. So that means that Alice's vote is a variable of 2 variables, the one for the one candidate, one for the other. And we also know that that they are friends, their friends relation. So we said Alice is friends with Bob, Alice is friends with David. Also, Bob and David are not friends. Bob is friends with Charlie, and David is friends with Bob. David is friends with Charlie, excuse me. So here we'll make an assumption that they make usually, I think it's homophily, it's called in social networks, that usually you interact with people of similar preferences. So the assumption that we make here is that if people are friends, they probably have similar voting preferences. But also, and that's the relationship that we know. There is a relationship, like similarity, but we don't know anything else about it. Okay, and that's what we're going to represent with the undirected graphical model. So first thing we're going to put in the graphical model, what are the random variables? And the random variables is the voting preferences of each person. So in this case, and I call it Alice vote, that means the voting preferences of Alice, 4 nodes, 1 for every person. And then within these nodes, we also define, as we said, this relationship that if they're friends, they're probably, their voting preferences are similar. So then we have an edge between voting preferences for Alice and voting preferences for Bob, which we introduce with an edge. Okay, and that's how we create the graph. And we only put the edges between the friends that we know. So that's how we created the graph. Okay. Now, in this graph, what are the clicks? We have to identify the clicks in this graph. So I would say, well, homework, what's not homework? They're actually easy here. The clicks are going to be the fully connected subgraphs of that graph. And in that case, it's going to be the edges. So there is a subgraph Alice and Bob, Alice and David, David and Charlie, and Bob and Charlie. Okay. Because we don't have any other edges to create a fully connected graphs. Okay, you agree on that? I take it as yes. So then, in order to define our probability distribution or these potential functions, we need to define a potential function for each of these clicks. Okay, and so I need to define a potential function between Alice and Bob, Alice and David, David and Charlie, and David and Bob. And that's what it does here. And these potential functions, so we see that I call it P tilde, just to say that this is the unnormalized distribution. We haven't put the normalized constant. So these potential functions are going to be for one for every click. And what these potential functions will define, it will try to quantify this relationship, like how strong is this relationship. So, for example, let's take the case of Alice and Bob, and yes, Alice and Bob. Then this potential function has to have there are two people, and each two random variables, and each one has two values. So we have to create 4 combinations, which is 1, 1, 0, 1, 1, 0, 0, 1. And say that one says it votes for candidate A. So in this case, define the function that if Alice and Bob vote, the relationship of Alice and Bob voting for the same candidate is 10. The relationships of voting, actually not only the same candidate, but the candidate one, the relationship of both voting for the second candidate is 5, while the relationship of them voting on a different candidate is in each case 1. Okay, that's how we define these potential functions. Now, as you can see, define these potential functions, it's a hard problem. It needs domain knowledge, and also even if you cannot define these variables, you have to define some functions with some parameters that you can learn from the inference. And once I have all these potential functions, then my probability distribution of my MRF, of my indirect graphical model, is going to be the multiplication of these potential functions divided by z, where z is the, as we said, the normalized constant, which is basically the sum of all these p tildes for all the combinations of the A, B, C, and D, where variables with A, B, and C, and D define Alice, Bob, Charlie, David. Okay, and that's how we defined indirect graphical models. We have the depends and con, but we'll describe them. Any questions here? Okay. Now, so what are the relationships that they are described by indirect graphical models? Well, again, they're not dependencies. What we define is independencies. So having the indirect graphical model, we can recover the independencies among variables is by looking at the direct nodes of the direct neighbors of each node. In this case, if the direct neighbors of each node are all observed, then the x is independent of all the other variables, given this the values of x's friends, and that's how we identify independencies in the indirect graphical models. That's why clicks are important here, because the clicks will tell you which are the neighbors. Okay. Now, this, as I said, in the independencies, you don't need to identify, because once you know the graph algorithm, you can define an algorithm, or there are algorithms that they can identify these independencies. Okay. Now, a comparison of Bayesian networks and MRFs. Now, MRFs are more powerful, but I put it in quotes, than Bayesian networks. And the case here of more powerful is that they can represent more real world situations, because usually there is a relationship between two variables, two values, two actors, but you don't really know what is this, what kind of relationship is this. On the other hand, they both can succinctly represent different types of dependencies. Examples we saw basically independencies, given we saw in the previous slides. The other thing is that I put it in quotes because there are independencies, and we saw examples that the Bayesian networks can define that MRFs cannot define, and the other way around. MRFs can be applied to a wider range of problems in which there is no natural directionality associated with a variable dependence. I told you that we usually have an idea that there is a relationship we can identify, but establishing that there is a causality or a dependency relationship is a much harder problem. On the other hand, computing the normalization constants in MRFs requires summing overall over a potential exponential number of assignments, because you have to sum over all possible combinations of all the variables. MRFs may be difficult to interpret. We saw it in our case, like how hard it is to create even an MRF for a very simple problem. And another thing is it's much easier to generate data from a Bayesian network when you know the directed, which is important for some applications when you do sampling, for example, or when you use the Bayesian network as a generative model, as we'll see in different tutorials. Okay. Now, some examples of the relationships that can be described from one type of the network but not from the other. The first one is similar to the example that we have. X is independent of y given y and z, and this is the dependence that we said that given the neighbors of x, the x is independent of all the other nodes. So x, in our case here on the left, has two neighbors, which is y and z, and there is also an additional node, w and z. It's also the additional node y. So we know that x is independent of y given w and z. Same thing for w. W has two neighbors, x and y. And there is also the node z. We know that y and z is independent of y is independent of z given x and y, and z is independent of y. Same thing given x and y. Okay, this relation, this simple relationship, cannot be described from a directed with a directed graph, as we saw in the graph on the left. Same thing, the V relationship that we described for a directed models where we have two nodes that have the same child, and we said that x and z is independent if y is not observed, and that's why so that's what the first thing shows. X is independent of z, but if z is y is observed, that means given y, then these two become dependent. This relationship again cannot be described by undirected graphical models, MRFs. Okay, so two basic relationships that we described in different these networks cannot be described from the other network. Okay, so we need both in order to be able to describe more relationships, because the other question I haven't answered is whether we can describe all the independence of a relationship. The answer is no. Okay. Now, before continuing, which is a different representations of these two big categories of networks, I'll again ask if anybody has any questions. Yeah. Okay. Now having these networks, there are some variants or different representations of these networks that are very important, and I'm going to briefly describe them here. One is what is called the moralized graph, and this is basically the way of converting a Bayesian network into an undirected form. So, and how we moralize this graph? We take a directed graph and we add side edges to all the parents of a given node, and then we remove the dimensionality. So, for example, for C on the left, there are two parents A and B. We add an edge between A and B, we don't have any more edges to add, and then we take out the directionality, and that's the moralized graph of the graph on the left. And these graphs are important. We'll see in the next tutorial, because they're used in many inference algorithms. Now, when we do this conversion, of course, we lose some of the dependence relationships that the graph is describing. Okay. Now, conditional random fields is another, it is a family or a subfamily of MRFs. This is very important in practice because they're used a lot in practice. And the conditional random field also is an MRF over two kinds of variables, x and y, which specifies a conditional distribution between the variables x given the variables y. So in this case, as we said, it's a discriminant form of an MRF where some variables are defined given some other variables. Okay. Now the function is pretty much the same. The functions, like we have potential functions and we have the normalized constant. Now, in most practical applications, we assume that the potential functions are of a form. What this form shows is basically log linear models, and that's where Themi's question comes from. The potential functions for conditional random fields are log linear. The probability distribution is log linear. And such distributions are common in supervised learning settings for which we are given some input and we want to predict a lot of, so we have a lot of variables that we are given and we want to predict another set of variables. And this setting where we have a lot of variables and we have as input a lot of variables and we predict a lot of other variables y, it's called structure prediction. So conditional random fields are used there very much. Okay. And
so Foula, one question.
Yes.
So why are conditional random fields a separate thing? So they're a special case of MRF. So when we talk about conditional random fields, do we talk about a special case that is easier to compute? It has it involves different sets of techniques for computing the probabilities. Why are CRFs different?
Yeah, I say special case. There are two main reasons. Well, one and a half. We'll see why. As when we described the MRF, you saw that the end probability distribution that we got is the joint probability distribution of all the variables. So the one thing here is that what we define, if you see the first formula, is we define a conditional probability distribution, which is the probability distribution of x, a set of variables, given the probability of, given the values of another set of variables y's. So that's the one difference. So MRF is usually a joint probability distribution. CRF is always a conditional. Okay, and the other not difference, but their how to say special cases is what kinds of exponents of potential functions they are used in practice, which is basically these exponents of a linear function. So they're log linear models. Okay, that's the two differences. The form of the potential function makes them gives the ability to define specialized inference algorithms which are more efficient. So there are two things. One is what we defined with an MRF and what we defined with a CRF. And another is what in practice we use for potential functions.
Okay, thanks. So I assume that CRFs are easier to compute, and therefore probably different sets of techniques are used to compute them, right?
So in general case, no, they're easier because they're log linear models. It's not because they define a conditional probability distribution. Okay. So yes, they are easier, but only because in practice we use potential functions for this. the potential functions are these exponents. Yeah. Okay. Now, another variance of graphical models is what we call a factor graph. A factor graph is a bipartite graph. First of all, factor graphs can represent both undirected graphical models and graphical models. And the difference is that the graph now defines the probability distribution. So of the graphical or the indirect graphical model, and we lose the dependence, the independence assumptions that we can identify for the graph, but we can identify it some other way. So the factor graph is a bipartite graph where one graph of nodes, so one group of nodes defines the random variables, exactly as in indirect and direct graphical models. Another group of variables defines the potential functions, factors, which are the how this which define basically the probability distributions or the unnormalized probability distributions that combine the adjacent variables. Okay. And if we have this variable, if we have this structure, then we have all the information to describe our unnormalized probability distribution, which in this case is going to be the unnormalized probability distribution, is going to be the multiplication of all the factors that we have in the what is called in the graph. And also from the graph, we know that these factors, even if we don't know them exactly how they look, we know that which functions they participate in each of the factors. So for example, looking at factor 1, we know that the only adjacent variable is x1, so the factor 1 is a function of x1 only. Okay, and if these functions define probabilities, then the unnormalized probability distribution, the joint becomes then the actually probability distribution. Okay. Factor graphs are very important, again, because once you define you convert your undirected graphical model or direct graphical model into a factor graph, there are inference algorithms, notably the message passing algorithm that perform efficient, well, a semi-efficient inference. Okay. Well, here what we mean by inference is basically identifying marginal probabilities. So what's the marginal probability of x1? As we'll see in the next tutorial. So factor graphs, you can think of them as internal representations of your directed or indirected model in order to perform inference if you use this message passing inference algorithm. Okay. So even if you don't define it from, that is your input, and you probably it will be defined as an internal representation as part of the inference process. Okay. And latent variable models, these are not new kind of models. They can be either directed or undirected. But what is the distinction here is that some of these variables, they are never observed. What's the difference here is that when you have variables that you cannot observe, obviously you can model a lot more things. I'll show an example. But then, because you never observe these variables, you don't know their values, training becomes much harder, because then you have to train with variables. You have to perform variable training, find the parameters of your probability distribution without having everything as known. Like without having all training data available. Okay, and as I said, can be either directed or indirected. And I'll give a simple example. Is that to say that I want to represent, to model the probability distribution of the outcomes of a coin when we flip it. and the coin can be biased or unbiased. Okay, if we know that's biased, then what is called different, the probability distributions of coming, so the outcome is different between the between the two cases, whether the coin is biased or unbiased. Like if it is unbiased, it's a coin, it's 50% to see its outcome, heads or tails. But when it's biased, it's a different probability distribution. So when we don't know whether it's biased or not, in order to represent this problem, we'll have to represent it with a probability distribution, with a graphical model, in this case with a direct graphical model, because the outcome directly depends on whether the coin is biased or not. And in this case, so we will create a direct model with is biased along with the different outcomes for n cases. And in this case, the is biased variable is what is called in unobserved, like we'll never identify, we'll never observe this variable. We can identify, there is way to define a probability distribution, but we never observe it. While the outcomes we can see whether this flip gave heads or tails. Okay. And that's basically an example of a latent variable model. And the last one is a graphical models with continuous variables. As I told you, so far, I'm making the assumption that the random variables are discrete. They're either binary or they have a finite number of values. In the case of the continuous variable, graphical models with continuous variables, obviously some of these nodes represent continuous variables. Usually, when you say graphical models with continuous variables, you assume all of them are random variables, and if there is a mix, you call them mixed. But I don't make this distinction because both of them are very challenging to perform train and inference. On the other hand, some very powerful models like the Kalman filter, which is ubiquitous in a lot of applications, as well as the Gaussian Markov random fields, are examples of graphical models with continuous variables. By the way, Gaussian Markov random fields is the bread and butter in spatial statistics. And as I said, training and inference becomes very challenging, as we'll see in the next tutorial. And so usually what people do is that they define specific PDFs, for example, multidimensional normal, that then they can perform some kind of practical inference on the variables, like identify the parameters. Okay, and that concludes my talk. And at this time, I'll take any final questions if there are. Yeah. I don't see, so I think, let me stop recording.